Hey everybody, let's talk about dilations off the grid. So remember, a dilation is a transformation that changes the location of a point. It doesn't make points bigger and smaller, it just changes their location, because each point is going to move along a specific distance, along some ray or some line from the center of the dilation, and it moves depending on the scale factor. So this was from topic 1, where the point B transformed to the point B prime by moving along this ray that goes through the points A and B, where A was the center of the dilation, and it moved to this exact spot because it has to be on this ray, and it has to be twice the distance that from A to B than A to B prime. Okay, another thing that we talked about in topic 1 was how dilations produce similar figures. Similar means that they have the same shape or angle measures, but not always the same size or distance. So here, the triangle J prime, K prime, L prime is the image of triangle JKL after a dilation with a scale factor of 2, centered at the point O. So all the corresponding angles are congruent. Angle J is congruent to angle J prime, but the corresponding sides are not equal. The length from J to K is not equal to J prime, K prime, but they are proportional to each other. And the proportion is based on the scale factor. For example, the length from J prime to L prime is 12.4, when the length from J to L is 6.2. That's double the length here because the scale factor was 2. And kind of going along with that, that similar figures have corresponding sides that are in proportion. So the proportions always have to be consistent. You can write them as ratios from the pre-image to the image, or you can write them as scale factors from the image to the pre-image. But notice how in this one where the sides are written as ratios, all the sides of the same triangle are on top and all of the sides of the other triangle on the bottom. Whereas here, the scale factors, it's always image sides over pre-image sides. So we got to make sure that we're consistent when you're writing your ratios in your proportion, and then also that you have corresponding points and sides matching up with each other. Okay, so after this lesson, we're going to review finding a center of dilation and a scale factor. We're going to practice writing corresponding sides in proportion like this, sides of ratios or sides of scale factors. We're going to learn about the ratio of perimeters for similar figures and the ratio of areas for similar figures. And to do that, we're going to use this link and answer some questions. So go ahead and click that link and meet me in GeoGebra. Okay, so in this picture, we have triangle B prime, C prime, D prime is the image of triangle BCD after a dilation, and we're going to answer a series of questions based on that. So first, we're going to find the center of the dilation and label it point A. We're going to determine the scale factor, and then we're going to talk about perimeters and areas. So let's start by finding the center by drawing some lines or some rays through corresponding points. Go ahead and do that now. So you can see on my diagram, I drew rays through D prime and D, a ray through C prime and C, a ray through B prime and B, and then I have this point right here. I just need to change its name to the point A. Then I'll use this to determine scale factor. Well, scale factor, remember, is a ratio of an image length divided by a pre-image length. So let me go ahead and do some measurements, and then I can find that scale factor. Okay, so what you see I did here is I used the measure tool to measure the length from the segment, or from C to D, and then that of C prime and D prime. So those are corresponding sides. And then the scale factor is the ratio of an image length divided by the pre-image length. So the 8 divided by 3.3, I said is about, that's the squiggly equal sign, approximately 2.4. So about 2.4 is the ratio of these lengths as I have them drawn here. Now, the next thing we're going to talk about is perimeter, and perimeter is the sum of the length of each side of a polygon. So what I'm going to do is I'm going to measure all 3 sides of each, and then we're going to figure out what the ratio of the perimeters is. So I'm going to pause and then go ahead and measure all of those things. So you can see I have my perimeter. To find the perimeter of the larger triangle, B prime, C prime, D prime, I measured a length of 8, a length of 7, a length of 7.2. Add them together, you get 22.2. Now let's go ahead and find the length of the triangle BCD. Okay, and to find the perimeter of triangle BCD, I added the length 3.3 plus 2.9 plus 3, and I get a length of 9.2. Now, if we look at the ratio for the perimeter, so the perimeter of the larger triangle is 22.2. Sorry about my writing here, 22.2. So when I divide the perimeter of the bigger triangle by the perimeter of the smaller triangle, I get about the same exact number, 2.4, as what the scale factor was. And that makes sense on account of when we are finding the perimeters of the triangle. Perimeter is just a distance, just like measuring the distance from point to point. The perimeter is the distance of all three sides. So it's still a one-dimensional number. And therefore, since I'm just adding the three sides of the triangle, it's going to still, kind of follow along with the same scale factor as when we just talk about the length of each side of the triangle. But now we're going to talk about the area of the triangles. And area is a two-dimensional measurement. So I don't expect the area to behave the same way as the perimeter does with the scale factor, but let's investigate. So by using the measure tool, there's a measurement for area. So I just click on each triangle, and I had to move them out of the way so I could see them. But the area of the triangle B prime, C prime, D prime is 23.9, and that of the smaller triangle or the pre-image was 4.1. So if I measure that in a ratio, 23.9 divided by 4.1 is about 5.8. And what's significant about 5.8 is that is actually the length or the scale factor 2.4 squared. 2.4 squared is 5.8, and that's not a coincidence on account of area is dimensions squared, or it's squared units, whereas perimeter and lengths are just units. I'm going to just simply take the scale factor and square it to determine what the area of the image would be. When I know the area of the pre-image, I can multiply that by the scale factor squared to find the area of the pre-image. Okay, now that we have these 4 questions answered, let's get a screenshot of this, and then we upload this into our note document. Let me resize a little bit. Okay, now a couple follow-up questions. Did this dilation produce 2 triangles that were congruent to each other? I said, no, the triangles are not congruent because they are similar, because dilations result in objects that have the same shape but not the same size. So these triangles are not congruent to each other. Instead, they are similar to each other. Follow up, how does the scale factor for the dilation compare to the ratio of the perimeters from question 3? The ratio of the perimeters is equal to the scale factor. For question 4, how does the scale factor of the dilation compare to the ratio of the areas? The ratio of the areas is the scale factor quantity squared. And then finally, is this an appropriate proportion? I said no. The last ratio, this one that's over here, has to be flipped because we have to be consistent. We have a side of the pre-image divided by a side of the image, pre-image over image, but then this one got flipped around, image over pre-image. So to be consistent, either we need to flip the last one or the first two, to be honest. Either way would work to be an appropriate proportion. And then the summary, you see right down here, a little quick recap of what we just did, and that is dilations off the grid. Bye-bye.